Our closest galactic neighbor, Andromeda, sits about 2.5 million light-years away from Earth. Launching a conventional spacecraft toward it, traveling at 28,000 miles per hour, would take over 94 billion years. Even at the absolute cosmic limit, the speed of light, the trip takes 2.5 million years, far exceeding a human lifespan. We don't have a speed problem. The universe is simply too large for conventional travel. To reach another galaxy, we must find a way to make the physical distance shorter. The math required to do that already exists. In 1915, Albert Einstein finalized his field equations, providing a mechanical blueprint for the operation of the universe. When Einstein presented these equations to the Prussian Academy of Sciences, he defined the exact mathematics for how mass interacts with empty space. This illustrates the core physical principle of his math. Heavy objects, like stars and planets, physically warp the geometric grid of spacetime around them. Approaching these equations as an engineering blueprint reveals the literal instructions for manipulating gravity to build a cosmic shortcut. Building that shortcut starts with the Einstein-Rosen bridge, more commonly known as a wormhole. In 2 dimensions, it's a simple geometric trick. By folding space, distant points align, connected by a physical tube. But in our 3-dimensional universe, entering this tunnel doesn't look like a flat hole. It looks like passing through a glowing spherical doorway. While we have the plans for the tunnel, we still need a mechanism with enough intense gravity to violently punch that hole into reality. In 1916, Carl Schwarzschild used Einstein's equations to describe a point of infinite density, the black hole. A black hole is the engine for our machine. Its gravity forcefully pulls surrounding stardust, light, and a spacecraft into the tunnel's mouth. However, using a black hole as the entrance creates a structural failure. Arriving at a second black hole at the destination means you are permanently trapped in a region where nothing escapes. For the machine to work, it requires a specific type of exit door, an anomaly that forcibly pushes matter out and prevents anything from going back inside. In 1964, physicist Igor Novikov proposed a theoretical concept to solve this exit problem: the white hole. A white hole is the time-reversed opposite of a black hole. Nothing enters it. Instead, light and matter are violently expelled outward into space. The math is consistent, but it creates a physical contradiction. White holes appear to violate the second law of thermodynamics. Entropy is the universe's natural progression towards chaos. A white hole would impossibly reverse this process, taking a randomized cloud of particles and neatly organizing them back into a perfect structure. Our shortcut machine is currently stalled on the drawing board because the necessary exit door contradicts the established laws of reality. Despite the entropy problem, some astrophysicists frame the Big Bang, a massive eruption of matter from a single point, acting as the ultimate example of a white hole. Stephen Hawking proposed that black holes leak radiation and eventually evaporate. This creates an information paradox, as quantum mechanics suggests information cannot be completely destroyed. When a black hole eventually dies, the matter it swallowed must go somewhere. One theory suggests it erupts outward, briefly becoming a white hole. In 2006, satellites detected an intensely powerful gamma-ray burst in deep space, with no visible cause. It behaved exactly like a white hole suddenly appearing and vanishing. These inexplicable anomalies suggest that Einstein's math may be correct, even if our current understanding of physics is still evolving. If the one-hole design fails, the math offers alternatives like the Alcubierre drive. This concept physically warps space around a ship, contracting the grid in front of it and expanding it behind to move the space instead of the craft. To a modern audience, wormholes and warp drives sound like pure science fiction. But exactly 100 years ago, the scientific community dismissed black holes as impossible, treating them as bizarre mathematical errors on a chalkboard. In 2019, we finally photographed a real black hole, proving the math predicted reality. While human engineering hasn't reached the stars yet, the mathematical blueprints to build the shortcuts are already waiting for us.